Hello students and welcome to the lecture. So students, as we know that in the previous lecture we had started the discussion over the simple harmonic motion, and that was our part 1. In this lecture we are going to start with the part 2 of simple harmonic motion. Okay, like in the previous lecture we had discussed about the periodic motion, oscillatory or vibrating motion, and then we tried to connect it with the simple harmonic motion. So here, before starting this lecture, just let us make a quick revision of the previous facts. So we know our body exists in two forms, either at rest or in motion, right? So one thing that I had told you in the previous lecture, that whenever we talk about the simple harmonic motion, we always talk about it from the point of view of motion, like the body is in a motion, changing its position continuously. It is not at the same position throughout the time. It is changing the position continuously, right? Here, in the previous lecture, we had said that periodic motion is actually a connection of two words, motion and periodic. Motion, when we know the body is changing its position. For example, first you see the body at this, then. So here you can say the body is actually changing the position from place to place. It is in a motion, right? But periodic means when a time taken by a body while changing its motion from one place to another is same throughout it, then it is a periodic motion. Okay, and when we fix the boundary of the motion, means the extreme end, the body could not go beyond the extreme end and the mean position is the same, then it is a oscillatory or vibrating motion. And there we have gone through a very strong statement, that is a very important statement also. Oscillatory motion is periodic motion, but not all periodic motion oscillatory motion. Remember why? Because in oscillatory motion you can say the body repeating its motion again and again, but it's having one extreme point and it could not go beyond these points. All right, so that's why it is the oscillatory or vibrating motion, but this motion is having the time period and motion both. That's why these are the oscillatory or vibrating motion in reference to the periodic motion. But in periodic motion, it is not necessary that the motion is always oscillatory. If the body not having any extreme point and the body could even go beyond that extreme points, then this is only a periodic motion, not any kind of oscillatory or vibrating motion. Okay, so there are some facts that we have just revised. Now let's move ahead and see what we are going to cover in this particular lecture. So here the first that we'll talk about is characteristics of simple harmonic motion, total energy in simple harmonic motion, simple pendulum. Three things: characteristics of simple harmonic motion, total energy in simple harmonic motion, and then simple pendulum. We are not going to cover like what is the simple harmonic motion, because already in the part 1 we had covered it. Okay, so I hope you have revised the part 1 in the well enough manner before you have make yourself available here to discuss this lecture. As many times I have told you, I have reminded you, that is for your own benefit. If you are doing this, the things will be in your favor. If not, the things might be against you. That's it. So here, before starting this lecture, as usual, we have the small disclaimer that we are required to understood before we proceed further. So the disclaimer is like, the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Now, let's have a look over the characteristics of simple harmonic motion. That is also we call as SHM. Okay. So anywhere if you see SHM, please do not get yourself confused. It is the abbreviation of simple harmonic motion. Also, you can say short form of simple harmonic motion. So when a particle executing the simple harmonic motion passes through the mean position, this is the first case. No force acts on the particle. Acceleration of the particle is zero. Velocity is maximum. Kinetic energy is maximum. Potential energy is zero. So remember, whenever there is a particle that actually executing the simple harmonic motion, additional condition is it is passing through the mean position. Then these 5 things that are listed over here, that things could be happen. First, no force acts on the particle. Acceleration of the particle is zero. Velocity is maximum. And if the velocity is maximum, automatically the kinetic energy will be maximum. Potential energy is zero. So these 5 things you are required to remember and keep in your mind whenever you see any case where the particle that executing the SHM passing through the mean position. These 5 conditions will be there. Alright, let's go ahead. Second case. When a particle executing SHM is at the extreme end. It's not at the mean position. It is at the extreme end. For example, this is the particle. This is one extreme end, this is one extreme. Previously, it was at the mean position. It was not changing it. Right now, we are seeing this is at the extreme point. Okay, so the condition is differ over here. In such a case, acceleration of the particle is maximum. Restoring force acting on the particle is maximum. Velocity of particle is zero. Kinetic energy of particle is zero. Potential energy is maximum. So we could say if this is a particle and this is the one extreme and this is the another extreme, and this particle is now there. Okay. In such a scenario, the acceleration of the particle is at the maximum. Okay. It is at the maximum. Restoring force. So what do you mean by restoring force? What is the condition over here? So if you go back to the stress and strain, there I have told you about the restoring force while talking about the stress. Okay, like if you having a rubber band and if you are stretching it, we know the rubber band could be stretched, right? For example, this is the rubber band. This is in the oval shape. While stretching, this is the shape. Okay, so you are actually exerting a stress over the boundaries of this rubber band. Okay, you are actually showing a deforming force. But once you leave the force, again the rubber band will be in the same condition. Why? Because of the restoring force. So restoring force is that force which makes the thing to reach the original position there that was already. Rubber band, you stretch it, when you stop deforming force, it actually gain the original position or previous position it was in because of the restoring force. So restoring force actually takes the pendulum or particle back to the place from where it started. So not only the acceleration is get maximum, but also the restoring force acting on particle is maximum, so that the pendulum or any particle will reach the previous or mean position. Velocity is zero. In that case, velocity of particle is zero. And as I have told in the previous, that when the velocity of particle is maximum, kinetic energy of the particle is also maximum. In that case, when the velocity of particle is zero, kinetic energy will also be as zero. Got it? But potential energy, previously it was zero, now it is maximum. So here, let us quick revise kinetic energy and the potential energy also. So kinetic energy is that form of energy which develops in a body when the body is in the motion. Okay. For example, just pick a ball and throw the ball towards your friend. Okay. Once the ball hit your friend, then your friend will complain about it because he will feel any kind of pain. This is not an, you can say, good habit, but just for example, you can say, kindly do not try it. Okay. And even if you want to, then you can take a plastic ball, that light plastic ball. Please do not go by the leather or synthetic ball. Okay. It is highly unrecommended. So if you pick a ball and you throw it towards your friend, what happens? The ball will get a motion. The ball will get a motion. And when the ball will get a motion, automatically the ball will acquire the kinetic energy. And once the ball hit your friend, that kinetic energy will transform into the another form. Okay. But the fact is that while in the motion, the ball develops the kinetic energy, right? Here, the particle is at the extreme end, which means the particle is not in a motion, hence the kinetic energy will be zero. Okay. Now, second case, potential energy. Potential energy is that form of energy which develops in a body when the body is having a particular height, particular angle, or any particular dimension. Or you can say just because of the potential of the, just because the position of the body, the energy develops, that is known as the potential energy. For example, have you ever thought like how the hydropower plant works? So basically in hydropower plants, in the dams, you can see the water stored at the top. Turbines are below. Then the water released on the turbines, and then the turbines revolved. And while they revolve, that mechanical energy transferred into the electrical energy, and thus the electricity produced. Okay. So when the water stored at the top, the water is getting a particular height or particular position. So then the water acquires the potential energy. When we release the water comes down. That potential energy transforms into the kinetic energy because previously the water was in a rest state. Now the water is in a motion state. And when it hits the turbine revolves. So mechanical energy, kinetic energy transforms to the mechanical energy. When the mechanical energy starts, automatically it gives rise to the electricity. So mechanical energy transferred into the electricity. So we could say potential energy into kinetic, kinetic into mechanical, and mechanical into electrical. Okay. So here, the particle is at the extreme end. So the particle is having particular position. So because of that particular position, the particle acquires a potential energy. So that's why the potential energy is maximum. So remember, whenever you're getting any case where the particle that is actually executing the simple harmonic motion is at the extreme end. So remember these 5 cases, the acceleration of the particle will be maximum, restoring force acting on the particle maximum, velocity of particle 0, kinetic energy of the particle 0, potential energy is maximum. Thereafter, the direction of displacement is always away from the main position, where the particle is moving away from the main position or coming towards the main position. Similarly, magnitude of displacement at any instance is always from the main position. Velocity of the particle executing SHM will be V equals to omega into under root A square minus Y square. At mean position, Y equals to 0. Then V equals to omega A maximum. So remember, here, direction of displacement, that is always away from the mean position. Whether the particle is moving away from the mean position or coming towards the mean position, the direction of displacement is always away. Okay. Whereas magnitude of displacement at any instance, whether going away or coming to the mean position, it always from the mean position. So this is the case that we are required to understood or keep. Direction displacement always away, whether coming or going. Magnitude of displacement always towards the mean position. The velocity of the particle that is actually executing the SHM or simple harmonic motion is this one. V equals to omega into under root a square minus v square. At mean position y is 0. Then v equals to omega a, that is the maximum. At extreme position y equals to a. So at the extreme position y equals to a and v equals to 0, minimum. Thus the velocity in simple harmonic motion is not uniform throughout the motion. This is another important point. The velocity of the particle that is actually executing the simple harmonic motion, that will not uniform throughout the motion, that will change. The direction of velocity either towards the mean position or away from the mean position. That is also possible. The acceleration of the particle executing the simple harmonic motion, a equals to minus omega square y. Okay. At mean position, y equals to 0, a equals to 0 minimum, y equals to a equals to minus omega square a maximum. Thus, in simple harmonic motion, the acceleration is not uniform throughout the motion. So velocity is also not uniform. Acceleration is also not uniform. They both are not uniform throughout the motion in the simple harmonic motion. The acceleration in simple harmonic motion always in opposite phase to that of displacement. As the displacement of the particle in simple harmonic motion at an instant is directed away from the mean position, and acceleration at that instant is directed towards the mean position. So there is an important fact. So here we are getting two important things: acceleration, displacement. Okay. So remember, this is a particle and this is the mean position. So displacement is that and that. So these arrows that I have drawn from green line, that are actually showing you the direction of displacement. These black arrows that you are seeing that are beside this drawing, these black arrows showing you the direction of acceleration. Now what you are getting? Come on, what are you getting? Just think. Are they in the same direction? No. They are in the opposite direction. That is what this para is trying to tell us. Whenever the acceleration and displacement considered in the simple harmonic motion, remember they both will be in opposite phase to each other. The displacement will be like this, acceleration will be like this. The displacement will be like this, acceleration will be like this. Why? We know that this is the case, but why? What is the cause? So if we go beyond the fact and if we try to find out the cause, remember, displacement is always directed away from the mean position. That is the mean position. Okay. So if the particle is going towards this or this, so this is actually taking the displacement and that is away from the mean position, right? The mean position is not getting satisfied here. Whereas the acceleration is always towards the mean position. If the particle is there, the acceleration will be there towards the mean position. That is what same written down here. The displacement of the particle in simple harmonic motion at an instant is directed away from the mean position, as I have shown you. Acceleration at that instance is directed towards the mean position, as you can see. Okay, so this is an important fact for acceleration and displacement in respect to the simple harmonic motion. They are always in the opposite phase. Displacement to take the particle away from the mean position, acceleration always towards the mean position. So because of this contrast, they always acquires a opposite phase. The velocity in simple harmonic motion is in phase with acceleration. When particle is moving from the extreme position to mean position and is in opposite phase with acceleration when particle is moving from mean position to extreme position. So here we got another fact that the velocity in simple harmonic motion is in phase with acceleration. So there are two cases. First, the particle is moving away from mean position to extreme end. Second, it's coming from extreme end to mean position. In such a case, what is the relationship between the velocity and acceleration? Let's see. So, when the particle moving from extreme position to mean position means this, extreme position to the mean position, the velocity is in opposite phase with the acceleration. Okay. So if the acceleration is this side, the velocity will acquire that side. Okay. Opposite. Whereas if the particle is moving from mean position to extreme end, this case, that was the mean position, that is the extreme end. Then, okay, there's a slight mistake you can say. So in a simple harmonic motion, when the particle is moving from extreme position to the mean position, extreme position to the mean position, this one. Okay. So velocity will be in phase of the acceleration. Both the phase of velocity and the acceleration, they both will be in the same line. But in the second case, when from mean position to extreme position, the acceleration will always towards the mean position, whereas the velocity will be opposite to the acceleration. Okay. So that is the relationship between the velocity and acceleration in the simple harmonic motion. Extreme to mean, both in same. Mean to extreme, both in different. After finishing the characteristics of simple harmonic motion, let's take a look over the total energy in simple harmonic motion, SHM. So how do we say what is the total energy that is occurring in the simple harmonic motion? So a particle executing the SHM, simple harmonic motion, possesses two types of energy. There are two types of energy: potential energy, kinetic energy. Okay. So even if we go back to the first cases where executing SHM at mean position, executing SHM at extreme position. So we see the role of potential energy and kinetic energy there, right? So that's why we could say the particle that is actually executing the SHM, that possesses two types of energy, potential and kinetic. So potential energy, this is on account of displacement of the particle from its mean position. That is the mean position. The particle reach here. So actually it is changing the phase, displacement. So when the particle will be there, we know the potential energy is maximum, right? Kinetic energy, this is on account of the velocity of the particle. So the particle requires a velocity to go at the extreme point. When this is the scenario, kinetic energy would be there. Okay. In simple harmonic motion, total energy of the particle is constant at all instants, which is totally kinetic when particle is passing from the mean position and totally potential when particle is passing from the extreme position. So we could say, as per the law of conservation of energy, the total energy of the particle is remain constant in simple harmonic motion at all instants. Like when the particle is at the, okay, let me show you here. When the particle is at the mean position, kinetic energy is there. When the particle reaches the extreme point or extreme position, okay, it's total potential energy. Kinetic transform to potential and then potential transfer to kinetic. So the energy will not change in the simple harmonic motion that will remain as it is throughout the motion. The frequency of kinetic energy or potential energy of a particle in simple harmonic motion is double than that of a particle in linear simple harmonic motion. The frequency of total energy of particle in simple harmonic motion is 0. The average value of kinetic energy or potential energy of a particle that is in the simple harmonic motion in a time of one complete oscillation is KEV equals to UAV equals to 1 by 4 m omega square A square. But the average value of total energy of particle in simple harmonic motion in one complete oscillation equals to EAV equals to half m omega square A square. At mean position, total energy of the particle in simple harmonic motion is in the form of kinetic energy. At extreme position, the total energy of the particle in simple harmonic motion is in the form of its potential energy. Expression for time period t equals to 2 pi by omega equals to 2 pi into under root m by k, you can say, where m equals to mass and k equals to force constant. So remember, when the particle is at mean position, the total energy of the particle will be in form of kinetic energy. When it is in extreme position, total energy of the particle in SHM is in the form of potential energy. That is what we have just read, so there is nothing to be explained here. A simple pendulum. Now, last topic to be discussed, simple pendulum. Simple pendulum is the most common examples of bodies that executing the simple harmonic motion like this. In the pendulum clocks, you have seen this kind of thing. This pendulum goes here, coming here, then goes here, coming here, right? This is what. An ideal simple pendulum consists of a heavy point mass body suspended by a weightless, inextensible, and perfectly flexible string from a rigid support about which it is free to oscillate. Like this one. This is the heavy weight, this is the rope, and this is the thing, rigid support provider, and with help of this, it will freely oscillate. Okay. This is the ideal definition of simple pendulum. Practically, a simple pendulum is made by suspending a small ball that we call bob, this one, from a fixed support with the help of light string. So ideally, we could say ideal simple pendulum consists of a heavy point mass body suspended by a weightless, inextensible, and perfectly flexible string from a rigid support about which it is free to oscillate. But practically, simple pendulum is made by suspending a small ball called bob from a fixed support with the help of light string. If the bob of a simple pendulum is slightly displaced from its mean position and released, it starts oscillating in simple harmonic motion. Like this was the mean position. If you slightly displace it, it will go there, come here, go there, come here. So simple harmonic motion will start. Time taken in one complete oscillation, time period of oscillation is given as t equals to 2 pi into under root I by g, where I is the effective length, sorry, that is not I, this is the L. L is the effective length of the pendulum and g is the acceleration acquired due to the gravity. From equation t equals to 2 pi into under root Lg's power minus 1, we note that the time period of simple pendulum is actually independent of the amplitude of vibration, provided it is small, independent of the mass of the body of pendulum, depends upon the length of the pendulum and acceleration due to the gravity at the place of doing the acceleration. Important points to be remembered. As t directly proportional to under root L, therefore t must increase with increase in value of L. It does not mean that L is inversely proportional to t, will become infinite. In fact, the relation t equals to 2 pi into under root L's power Lg's power minus g is not valid for pendulum whose effective length L is more or less equals to radius of the earth. This shows that t increases up to a certain limit only. In special cases, if L equals to this, then t equals to 2 pi into under root re by g equals to under root 6.4 into 10 power 6 by 9.8 equals to 84.6 minutes. So this is another equation you can say. If we go by this equation, we could get 60 minutes. If we go by this equation, then we could say t will increase with decrease in value of g. As the value of acceleration due to gravity is less at hills or inside the mines, due to it, the pendulum clock will be slowed down. It means the pendulum clock will be losing the time at hills or inside the mines. If the bow of simple pendulum suspended by a wire, then effective length of pendulum will increase with rise of temperature. Due to it, the time period of simple pendulum will increase. Similarly, if the length of the wire decreases due to the cold, then time period of simple pendulum will decrease. If bow of simple pendulum is made to oscillate in some fluid of density where phi0 is smaller than phi, the density of the bob, then time period of simple pendulum gets increased. The time period of a pendulum clock in a satellite or lift falling freely under gravity is infinity. There is a note. A clock is said to run slow when time period of its pendulum increase. On the other hand, it is said to run fast if its time period decreases. Second pendulum, if we talk about, it is that simple pendulum whose time period of vibration is 2 seconds. The bob of such pendulum while oscillating passes through the mean position after 1 second. Putting t equals to 2 seconds and g equals to 9.8 meters per second power minus 2 in equation, then we could get it as 99.3 centimeter. Hence, the length of second pendulum where g equals to 9.8 meters per second power minus 2 is 99.3 centimeter. The length of second pendulum changes with the change in the value of acceleration due to the gravity from place to place. Note, a second pendulum is also phrased as a pendulum that beats second. So here we have finished the simple harmonic motion. It is requested to all of you kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.